everyone. So today let's start with a problem analysis of yesterday's problem, and after that maybe we'll discuss some more related problems. And I think we don't have to discuss each problem, because there are some problems that were solved almost about by everyone, and if you still have troubles with one of those problems, I believe it will be much better if you just ask one of your friends. It will be beneficial for both you and the one you're asking. So now let's start discussing more hard problems that you got more troubles with. So let's start with problem B. So this problem we had two convex polygons, and we had to find the pair of edges with several requirements. That first they should be parallel, and second that there should be a segment that connects some points of these edges, which is not intersecting the both polygons. And which is also has a angle of 90 degrees for both of the edges. So the first more strong requirement is that the edges should be parallel. So we can prove that for each edge and the one polygon there should be at most two parallel edges in the second one, since they are both convex and they are given in the sorted order. We can find for each edge the parallel edges from the second polygon. How can we do so? So probably we have to clarify what is parallel edges using some formulas. So let's see if for the edge of the polygon, let's just consider this vector, and then we could just normalize it, makes it the length equal to 1, and we can see that the other edge would be parallel if the same vector for this edge scalarly multiplied by this vector provides us the value 1. Yes. So, and for all other vectors, it's clearly would be not 1, and for if we have this edge, then by multiplication we'll get -1, and it's also monotonically decreasing from this point to this point and increasing from this point to this point. So we can use all those facts to improve the speed of our searching, and we can also use like a binary search approach for each specific edge. But since we are looking for, we need to check for every edge, it is better to use optimizations with pointers. So we're just starting with some one fixed edge. After that we could find the vector which has more the largest value with the multiplication of our current one. So let's call this vector AI. We are going to find the vector VG so that it is the largest possible. Actually, in this problem we are looking for this edge, but just to understand more, we can also look for both this edge and for this one. Actually, of course, in this problem we're only looking for this one, but I can show you that if you would like to find both of them, you could do this in the same way. So we are looking for the vector G that it maximizes the product. And similarly, here you would find the second edge which minimizes the product. And it is, of course, it is not always appears that this maximum value is 1. It's only would be 1 if these vectors are parallel, which means the edges are parallel. But still, once we found the maximum value, after we move to the next edge, we are keeping the pointer to the previous maximum. And since we know that for the next half of the edges, this function will be increasing until it reaches some maximum, and then it will start decreasing. So until for looking for the maximum, we can just move the pointer one by one, just checking while the product with the next vector is greater than the current one, we just moving to the next edge. And after the cycle stops, we'll stop at the vector which has the largest product with the current edge, and which provides us the potential edge what would be parallel to our current edge. And we're doing the same for the maximum for minimum. Again, I repeat that there's no need for the maximum vector. We can only look for the minimum one. But if, in your consideration, you are going to check both parallel edges, you can just find both of them. It still would be the same algorithm, the same asymptotics. And after that, you have to consider several cases. So once you have one edge and the one polygon, you have another edge, another polygon. You still have to check whether it's possible to find a point. So you can travel from one vector to another one with a straight degree. And the cases are not very hard. First, you just need to check that the segment does not intersect the polygons. It only appears in the case where the parallel edge is behind this one, like this. So you just need to check from which side of the line these points are. And the second, what you have to check is that the projections of those segments on the line intersecting. So distinguish this case and recollect this case. There is clearly no way to draw a segment. Yeah, I guess that's all cases we have here, and we're using pretty standard thing to find the vectors which have the largest value of the multiplication, or to look for looking the parallel edges. And again, you also don't have to use a scalar product, you can use the vector product. If there's a little bit different approach, so if you have this vector and this vector, you can not look for the scalar function. Instead, you can use a vector multiplication of those vectors, and by seeing the sign of the vector multiplication, you can understand whether this vector is to the left from this one or to the right from this one. If it's from the left to this one, so you probably want to go to the next pointer further. And if it's already to the right, to this vector, you should probably stop and check this vector and this vector for maximum. But they would be parallel only if the vector multiplication is 0. So there are kind of several ways. You can use a scalar function to use the maximum, or you can use the vector multiplication for looking for the 0 of the vector multiplication of those vectors. Right? So yes, that's all for this problem. If you have any questions, you can ask now or when you're ready. Next, problem D, was solved not by that many teams, but in fact this problem is pretty simple in my opinion. So I repeat you the statements. You have an array and you are looking for two non-intersecting segments. They have the same maximums. So let's first step what we are going to do is just for each index I, we're going to find the closest position in the left and in the right that has a larger value than AI. So in the picture, it will be like this. So look for this one too. It's just some pre-processing that we can do from the beginning, and we will use it later. And how to find those positions, there are also several approaches. Maybe one of the most common is to use stacks. So we can do this separately. Find the, for example, the leftmost. How we can do it? If when we're going from the left to the right, we're just storing the stacks of increasing elements, and once we have some smaller, when we have like this element, we are popping out the last elements of the stack and saving for them that the next element, which is smaller than it, is the current one. You can clearly see that if it would be the one which goes previously, then we will pop this element earlier. And since this element is popping this out, so it is smaller. That's how we can memorize for every element the next one which is closest and which is smaller. and in this sense we are going to find this next one which is larger, so it's like reverse. So we will store the decreasing stack and pop in by the larger element. So once we've done this, we're just going to consider some cases. First, let's just fix the value of the maximum. So let's say both first maximum and the second equal to this number. Then let's look at all the occurrences of this number in our array. So here's the T, here, here, here. We can again preprocess and store the whole list from the beginning, just for each value. We just keep storing the indices of the occurrences. And after that, let us fix what would be the right occurrence of the maximum in the left segment and would be the leftmost in the right segment. So first let's consider the case when these two occurrences are adjacent, like this. So here is the rightmost in the left segment and this is the leftmost in the right segment. Here could be the several cases. The first case is when here between those elements we have the one which is larger than t. So here's some larger. That would mean that our segment first can have the end position somewhere here between the last occurrence of t and this element which breaks us. And the left end should be again between the current occurrence of t and the closest element again which is larger than t. So if it's somewhere here, so the left end could be somewhere here. If you just know and it would be from the beginning. If it is here, then again it just constrains to only the element which is larger than t. And the same from this side, it's also measurable. And in this case, we can just calculate the number of the ways to pick this first segment multiplied by the number of ways to pick the second segment. They are independent in this case. The second case is that if there would be no such element which is larger than t, then for the left ends of the first segment and to the right end second segment, they are again independent. By the right end of the first segment and the left end of the second segment, they are become dependent since they will have to increase those indexes have to increase. So that's just again not that hard to compute. So this end is independent, this is independent, and two indexes are dependent only by the increasing constraints. So if we consider them independent, let's then just almost divide by 2. We will left with the correct answer, except like when they constraint. So we just divide by 2 and subtract the number of indexes. So just depict just binomial coefficient of this length. So that's another case. And what would happen if they are not adjacent? So if the leftmost will be somewhere here, and in this case we definitely will have the element somewhere between which is equal to t. And in this case, we will have the number of the second segments is just here. Again, we imagine what would be the constraint by the larger element here for this t, and pick the one which is closer this element or the next t. So in this case, the number of the left ends would be like this segment. If there would be no larger element here, then it would be larger until the next occurrence. And the same for the right end. We again are constraining by the larger element, but we're not constraining by the another occurrences. Yes, since we fixed and saying that this occurrence is only the leftmost. We don't care about the other occurrences from the right. So in the right, the constraint for the right end would be like this. And here you can again imagine that the number of ways to pick the segment that this occurrence would be the leftmost occurrence of the maximum is independent from our left segment completely. So in this case, we can just pre-calculate all those values for each occurrence on the right, and after that, when we are standing here looking for this occurrence as a rightmost in the first segment, we just will have to accumulate all the pre-processed values for the suffix. So since they are completely independent from this part, we can calculate them separately and then just use the accumulated sum. And that's all cases. First case is when they are adjacent and there is a larger element between them. First, second, write down. First, they are adjacent and there is a larger. Second, when they are adjacent and there's no larger. And the third one, we fix this one and all this to accumulate. Is it working? Oh, okay, I just need to touch. Any questions about this one? The third case? Yeah, sure. So, we fixed this one, the rightmost occurrence in the left segment. Yes. So we are not we considering that the leftmost occurrence of the right segment is not adjacent to this one, so it's not this one. So the right segment will start somewhere there. Yeah. So if we'll consider what would be the actual leftmost occurrence of the maximum, which is equal to t, then we will see that it is independent from the first segment, the number of ways to pick such a segment, and we can easily calculate it. For example, if we fix in the occurrence, we will not fix it, but we'll just zoom later. But well, let's first consider if we are iterating over this occurrence as well. So what would be the number of ways to pick the left end for the segment. We should not go before this position because this is leftmost, and also we could not go before the element which is larger than this, so otherwise this will be the maximum. So from these two indexes we pick in the maximum and make it the constraint for our left end. So it should start from here and would be something between here and here. And again for the right end we could not go further than the maximum, the larger element than the t. So it will be like here. But here I don't care about other occurrences of t, because here we cared because we consider this is the leftmost occurrence. But since we don't care about the other occurrences, we are not considering other occurrences, but only this constraints the position of the element which started. So to count the number of segments that has this occurrence as the leftmost, we're just taking this length and multiply by this. And it's completely independent from the first segment, so we can recalculate these values for all occurrences at the beginning, and after that when we're staying here we just need to accumulate the values for all occurrences except the next one, which we can just store the sum on the suffix. Any more questions? Let's talk a little bit about problem E. It wasn't the hardest one. So we have some points. We had to split them into 3 groups. So that's the total distance between the point to the sync point for its group is totally minimized. So first, the obvious observation is the group will be split by the segments if the points are sorted in order. Yes, so there's no point to move this point here and this point here. Otherwise, we could just swap and decrease the total distance. And but still, it is not very clear what would be the sizes of the first and of the second group. And I guess the idea for this problem was we just try all possible sizes of the first group. So we just take all these points here. And for all other points, first we're looking for each point what is the closest point, second or the third. And first we just trying to separate them to optimize the distance for each point. But after we did it, it would appear that we could exceed the allowed amount of the points for some group. So here, for example, it is 2, but we took 3 points. In this case, again, we're doing greedy, and we just move all the extra points which are not filling into this group to the next one. So we calculate that we should move 1 point, and we're shifting the pointer which leads the points into the group to the left. And after that, that's the best thing we could do about filling into the constraints about capacity, and obviously the points are matched optimally, so there's no other way how we can swap anything to improve the total distance and still fill in this constraint. And after we found what would be the bounds by our assumption of the peaking size of the first group, to actually find the total distance, we can take this point again, split the segment by the two, just by this coordinate, and to calculate total distance we'll have to add coordinate of this point multiplied by size of this segment minus the sum of the coordinates on this segment, and for this it will be opposite, the sum of the coordinates of the points in this segment minus this coordinate multiplied by the number. So this also can be reprocessed by the prefix sums, and this bound we can find by the research. Yes?
Is it possible to use ternary search to find the second boundary between...
I don't know.
Okay.
Possibly it can work, but since I don't know how to prove, I would not be sure. The next problem F. Again, we're not discussing every single problem, just the most interesting, in my opinion. So, in this problem, we had a tree. And here we had some events that some point become infected and the infection spread by the edges, and we kinda ask in this problem to model this spreading of infection and look for the moment where the number of unaffected connected components is the maximum possible. So again, we just doing the simulation by storing some events in some prioritized data structure. So there would be events of the two types. The first event type is when the vertex EV becomes infected. For example, if you know this vertex became infected, either by some edge or from the beginning, we know that for all adjacent vertices, they could become infected in the time. So if this would be time t, then this would become infected in the time t plus the weight of this edge. Of course, it could appear that it will become infected earlier, but still we're just pushing this event to our data structure. And from the all events events, we always take the closest with the event with the smallest time. So if there will be another event that says as this vertex becomes infected, we will just consider it before, and then we'll just ignore this one. And there is a second event. It is about the edge. The edge could also be infected, and if it is the edge that is getting infected by the both sides, so here it has infection on the one side, and this vertex also becomes infected, we would know that when some time passes, the whole edge becomes fully infected. It's another event time. Edge becomes fully infected. When this event appears, we have -1 to the total number of unaffected components. And when the first event appears, the number of unaffected components will increase by the number of unaffected edges adjacent to this vertex -1. So in this case we'll have plus like this. And that's kind of everything we had to do with about the problem. Just carefully store the events, and that is all, I guess. I don't know what else can we say about it. And yeah, you have a question? And I guess this problem even could be solved in more hard variations. What's the problem similar to this one that I want to discuss with you? We will discuss it later, but I will just define the problem right now. We have the tree. And we have several queries to remove an edge from this tree. Obviously, the tree becomes the set of the trees after one or more such queries. And after each query, we have to output what is the sizes of the components that are splitted from the current component. Are you familiar with this problem? Okay, then probably you will be interested. And so I will just rem edge and output size in and size up. And the important thing that with the queries we have to process online. So that is a problem we will return to, and for now let's just keep discussing problems. Oh, the next problem was a little bit dirty one. So we were playing a game on the set formula. players were playing a game, and by one turn just sets previously unset variable to either true or false, and for the first player he will try to make that the formula will become the false in the end, and for the second he will try to make that this formula will become a true. So as you can imagine, there will be a lot of cases in this problem. The first case I illustrated here. The important observation is that if some variable appears into in the pair with the different variables, this would lead the first player to winning regardless of what the pairs are. So there could be two cases of such, two sub-cases of such a case. The first case is when this variable appears with the same sign in both pairs, and the second one when it appears with the different signs. So in the first one, the first player should just make the x equal false, which means that the second player have to make both true, this one and this one. And of course, this case should be like symmetric. If it has both negative sign here and here, then we will just make it true, and we will just make. But let's just keep it a little bit simple and say that here they are all these are positive. So the first player turns into the x equal to false, and after that the second player have to make both this variable and this variable equal to true. But he cannot do this in one turn. So the second player would say this, and the third will say this. And after 3 turns, the first player would win. And what about this case? In this case, the first player should start with this variable and make this false. This forces the second player to satisfy this pair by making the x equal to true. And after that, the second player, since this variable is set and this equals to false in this bracket, so the first player will just make this variable also false, and again wins on third turn. So that in all the cases when some specific variable appears into the pair with the different variables, the first player will always win in not more than 3 turns. So let's go further. Now we consider that there's no such case where the variable appears in the pairs with different variables, which means that the variable could appear just by itself, like this, or all the variables will be split into pairs and appear only with its pair. So this. But so it could be several pairs with different signs, but the variables will be the same in this for some specific x and y. They will not appear with anything else, only with each other. And so we can actually take all these pairs of this x and y and find out what is the function that is made from these pairs. So clearly this part is just some Boolean function, and we can basically find out what exactly is a Boolean function from two variables. And again, here come several cases. The first most simple case is when the function from two variables x and y can be set to false in one turn. So that is a function like x, y, false, or x and y. And again, and everything we can produce by reverse. Like this is also can be set to false in one turn. And of course, there's some functions like this, but this is just, again, it can be produced from this one by switching the signs. So there could be the formulas that can be set to the false into one turn. This means that if there is such function, the first player again just wins at the first turn. Second type of functions is just disjunction. For this type of formula, when the first player enters it, so it doesn't matter first player or the second player, he will just set the variable the way he would like to see it. So the first player will make it false, the second player will make it true. And after that, opposite player should always make a move into the second variable and set it to the opposite value. So it appears that all these functions are not affecting the result of the game in any way. Once one player enters it, the second should always make one more move into that, and in the end they will just continue playing without this pair. So these pairs do not affect the game in any way. And the third type of function is a function like this. Either this or this. What about this one? Once the first player I forgot what about this function. Again, if the one player makes a move in this, then the second should place another variable. Let me check what is the case. if the first player make a move into this pair, then the second just can make the move that sets this formula to true, which is good for the second player. So there is no point for the first player to make a move into this pair, but if he forces the second player to make a move here, he would win. So the only way how the second player can survive and not lose the game, if all the moves into this pair will be starting with the first player. So if there is some pairs, maybe the second player does not want to start moving into this pair at all. So he would play anything else, and once the first player makes a move into this pair, he will just remove, again make an alternative turn into this pair to just remove the pair, because that's the way how the second player can lose the game. And this means that the winner of game defines by the just player who will be forced to, not the player, but whether the second player will be forced to start this pair. And it appears that if this number of all other variables is odd, then the first player could always force the second player to start this pair. So he will just make a move into all other variables, and the last variable would be by the first player, and the second player will have to make a move, and he will make a move into this pair, and after that the first player would make this pair set to false. Yeah, so we have described all the ways how the first player can make the formula set to false in the end, and in all other cases the second player wins. I know it's a little bit confusing, too much cases, but if you have a question, we can try to think about it once again. So, for all these cases, the first player wins. For this case, also first player wins, and for if there's this pair, so first wins if the n is odd, and in all other cases the second player wins. If there's no questions, let's take a 10 minutes break and discuss the last two problems after that. Okay, let's finish with the rest of the programs. Problem I, you had a specific graph as the input, and it has described that the graph is specific, correct, how it says in the statement. If it is either a combination of the two correct graphs connected like this, or two correct graphs connected like this. And for this given graph, you had to count the number of spanning trees. In other words, number of subset of edges which makes a tree. And that's all. So I did not get the solution by myself. So I checked the editorials for this program. I can try to describe what I could understand from it. And the first thing, what the author proves is that in the correct graph with at least two edges, then there would exist either the vertices of the degree 2 or the two parallel edges. And I guess you can prove this just by induction, this fact, and it's not hard to just consider two cases. How do you get this graph? And well, yeah, that's all. But what then the authors are saying for us to do is, since there is either this case or this case, we can just simplify our graph. In the case when we have the vertex of degree 2, we can just replace it with the one edge, and the same with the two parallel edges. We can reduce it to again one edge. And the one thing I could not understand is that why, after we simplify the graph, it is still correct. That's one missing point for me. But if we suppose that after we simplify our graph by using this replacement and it is still correct, then we can continue this process and find again one of these two cases and continue some simplifications. And by the idea, in the end, you will be left with exactly one edge, and not tell anything about counting the answer. So during the process, for every edge, we will store two numbers, f and p, where f would mean that the number of the ways to make a tree from the graph which has compressed to this edge, and p is the number of P is the number of the ways to make a tree from the edges that's compressed to the edge without taking one edge. So this number is for number of ways to make a full tree, and this is for the making a tree without some one edge. And
speak a little bit louder.
Okay, sorry. Let me repeat. F is the number of ways to make a full tree from the graph, which is compressed to this one edge. And the P is the number of ways to make tree without one edge. So let's see how we can recalculate these values after compressing our graph. So if we have this case, so for this, case, if we are going to make a full tree from this one, then it is just a product of the full tree of this edge and this one, right? So f, this is 1, e1, 2, so we are going to calculate fp for this edge. F is just a product, and P is just some. Here it is this full, and here is a partial, and vice versa. And let's see what happens to this case if we are going to create a full tree. Then we are taking the full tree on the one of the edges. Then for other we have to remove one edge. So it will be full for the one, and for the other one is removed, and the vice versa. And for the partial, it's just the product of two partial trees. So by compressing either two edges that are sharing the one vertex of the tree or the two parallel edges, we can decrease the size of our graph while storing these two numbers, and in the end we'll just look at the number f at our ending edge. And just to maintain all those operations, you have to use some data structures that allows you to delete edges, insert edges, and to search for the vertices of degree 2 and for parallel edges. So any data structure like map can work for it. So the main idea is pretty clear for me. Is one thing I couldn't understand why after this operation our graph is still considered correct. That's missing point for me. But if you making an assumption that it is true, then the solution should look like this. The next problem about javelins. Here you have to pick some, you have some sequence of javelins, and you have to pick some subsequence of it. And by the statement, it is described how the javelins work one after another, and after a little bit observation, you can notice that it is never, you should never pick a javelin which is larger than the previous one by its radius. So actually here we're going to consider only non-increasing subsequences, and what we need to find is just to look for non-increasing subsequence with the total strength, how to say, is at least k, and of total cost as small as possible. I think for me it's very natural to try to use dynamic programming for this problem. So the first parameter is almost for sure will be the size of the prefix we've already considered, and more precisely we can use the index of the last used javelin. So this index should be the last used javelin and what information else we need from the prefix. We can store just either the current cost of the all, or I guess the cost had the larger constraints in this program, so it is would be better to store the total strength of the javelins we have picked in the prefix. And among all these options, obviously, we only want to store the way, the subset of subsequence which has the smallest cost. Minimum cost. So let's see how can we calculate our function. So obviously when we are considering prefix without the last element, then the first element should be less than I, and the second one should be our current strength minus the strength of the last element. And the actually the previous Gemini would be any, right? So we can move to this state from any state that looks like this, and of course we will look for the minimum value among all of this, and in the end we'll just let's write it like this. After that we'll just add the cost for the last area. So here, by looking for the minimum, we have to find the minimum value at some prefix, right? So this is just a constant, and here is some prefix of the values. So we can do it like for the size of the prefix, or if since here we are not satisfied with the cubic solution, we have to use some data structure. And since we have two types, when you have calculated the value, you just want to set the point value as a point of array. Here is the second is just query on the prefix, which both can be solved by segment tree or Fenwick tree, which provides us square multiplied by log solution. So I think that's all. I don't think we have to discuss other problems in that many details. So if you're still struggling with some problem we have not covered, you can ask me or one of your friends, which is better for you. And also for the ones we have covered, if you still have questions, of course, you can ask me and we'll try to come to understanding. So I guess that's all for yesterday's problem. Now what I would like to discuss some more things, some of this problem and probably one more with you. So, did anyone get any ideas about this problem? Yes? Anyone? Okay. There is a pretty common, I'd say, trick. Maybe a lot of you heard about it. Is when we have several sets, or containers, doesn't matter, and we are going to merge them in any order. So we have queries to merge this pair, then merge the result with this here, then merge this one, and if these containers are, doesn't matter which, queues, arrays, or sets, or binary trees, if for any query to process it, we will just iterate over the smaller set and insert the elements one by one to the largest one. So in the end, the asymptotics will be only n log n insertions in total, where the n is the total size. So it's a pretty common trick, right? And it can be used in several ways. How you can solve a problem, maybe where it requires more hard solution, or just it's not very clear how to use it. So first, let's consider the problem, which looks like also have a tree, weighted tree. And we have some number L. And for this tree and for the number L, we have to check whether there exists a path of the length equal L. Have you seen this problem? So we have to find whether the pair of vertices exists. So the length, the sum of the edges between them equals to the L. And to solve this kind of problems, first we want to understand what is the path. So as we've talked like 2 days before, any path can be described like a path to the LCA, to the up, and then from the LCA down. So this only requires us to choose a root. So we arbitrarily take one vertex as a root, and after that we're making proper testing for all vertices to store like LCA. And, after that, if we're considering that our path will be between some pair of vertices, in the common case, it's just some subtree with a vertex U, so that the distance between U and the LCA, which we call Z, is some equal to some L1, and then the distance between V and Z is equal to L minus L1. So what we are going to do with that? For each tree, subtree, let's store the set of the distances of the all vertices to the root of the subtree. Right? So let's imagine that for any subtree we can store such a set of the lengths to the root. And when we are taking one node and making an assumption that this will be an LCA for our path, to check it, we have to pick 2 subtrees and like iterate over vertex in one subtree and check whether they exist the vertex in the other subtree with the appropriate length. You know this problem? No? Okay. So, and if the number of subtrees will be more than 2, so you'll just from this part you have to check for all other subtrees. Yes. Okay, so now let's try to optimize it somehow. Since it's what I have described before, it's at least like a square amount of memory, which is never going to be appropriate for this program. First, let's understand how can we store these sets. So if we have like some vertex and we have already have the sets for all its children, and if we have already checked whether the answer exists in all those subtrees, we do not actually need to keep these sets, right? So we will use them, the memories they're using and their nodes in these sets by itself to produce our set for this whole subtree. So how can we actually store this set? Of course, since we want to make a search into this, so we want to check if this set contains some specific value. This set probably would be better for us to be like binary search tree. It maybe could be something else, but let us say this will be a binary search tree or like set from plus standard library or tree set from Java. It doesn't matter. So just a binary search tree, and so set is a binary search tree, and we also want to make the operation. So let's imagine that we have only one child, and we want to make from this set the set for the whole tree. That's what everything what we have to do is to put to increase all distances from this set by the weight of the edge, and then put 0 into this. Yes. So to make this operation to proceed it optimally, we do not want to manually increase all the values inside the set, but we will just store some common constant for everything. So it will not be just set, but some constant which we assuming that we are adding to every element of this set. Yeah. Okay, so that's a simple case when we have only one child. But if we have several childs, let's do the same for every child. First, we'll just increase the constant for this set by the weights of the corresponding edges, and after that we just have to merge all of them into the one set, and name it that it will be the set for this subtree. And to do so, we are gonna take just the largest subset, and everything what is the rest we will just insert to the largest. And for inserting, we'll just iterate over all of them, just for every single element in the set. And when we are moving this element, like say x, we have to calculate its actual value. So we are going to add the constant from this constant, and since we're going to insert it there, we want to decrease the constant from the second one, since we are considering that we have increasing every value by this constant. And that's all how we merge it. And how we actually gonna find the answer when we are iterating. So since the answer is goes from the different subtrees, if the answer exists, we will iterate over one of the ends of the answer for this subtree. So let's check for the answer when we are removing one element from the one set to another. So if the element has a matching pair to the largest set, which we are merging to, so we'll just, before inserting it to the binary search tree, we'll just check whether there is a corresponding pair with the appropriate length in the larger set. But if after we have merged this set into this one, and then we are merging this set, it could be both that the second element of the pair is inside this set and this set. So since we have already merged all of them into the one set, so we can do it just by one query. And particularly for this problem, there is a tricky case when we do not want to consider a path that goes to the LCA and then it has some another end inside this subtree. So we still wanna, or actually it doesn't matter. Yes, we just first doing query and after that we inserting. So this pair will never appear, right? Yeah, so that's all. Even the case when the path goes from the one vertex to its ancestor will be considered if we will put the 0 immediately to the larger set once we have increased every value in it, inside it. So any cases will be considered. And what about asymptotics? Since we know that the total size of these sets is n, and we are just merging them, not and never splitting, so it will be in the total n log n moves of the one element from the one set to another one, and just to make queries and inserting into the binary search tree will have just additional work. So the total asymptotics for this solution will be like n square log. Is it clear? And this can be in like more other ways. For example, if we have a query, again we have a tree and each node is colored to some specific color, and for every subtree we have to count like for each color how many vertices has a specific color. We can do the same, just manually calculating the value for the subtree, and once we need to make up the answer for the larger subtree from the smaller subtree, we will merge them by moving all the vertices from the subtree which is not the largest to the largest one, and this will work the same. Okay, but let's move back to this problem. So here, instead of the mergings, we have splitting. So initially we have a tree, and then we have a query for removing one edge, and after that we need to answer what are the sizes of the components that are split from the component contains the current query. So let's imagine we had no this restriction. Then do you know how to solve it this way? Yeah, so we just reading all the queries, and we are looking what would be the set of the trees in the end, and we are just processing the queries from the end. So if we have remove edge, remove edge, remove edge, remove edge, remove edge, we are just looking what is in the end, and we're starting proceeding queries in the backwards. So this will become add edge, add edge, add edge, add edge, and in this way we can just use the digital union set data structure to keep the current size of the components. But if we do not know what would be the queries in the future, for example, we wanted to remove this edge. Since we know that this is one component, and after we remove the edge, it will be two components. So if we could make this query in a time proportional to the size of the smallest part, this would be good. Do you understand why? Because it would be like the same with the merging, but here it's just splitting. We just need to know which first. First, we would like to know which of the parts is the smallest. And for example, if we knew that, then we can just use some BFS or DFS for all these vertices, like recolor them into the new component, count what is its size, and just decrease its size from the size of the second component, which we are keeping as a counter for this color. But the only thing is we do not know what is the smaller part. So we can like kind of guess. I don't know how this is gonna work. But there is an interesting approach that allows us to find which of the parts is the smallest if we will use two BFSs. So we are starting to run BFS here and here, and we are processing two searches in parallel. So we are like adding this vertex to one queue in the BFS algorithm. So here's goes here, this one goes here, and after that we're looking for the current vertex, putting this vertex here, and this vertex here, then this vertex here, then this vertex here, this vertex here, and this vertex here, and then we'll see that our algorithm start working in the first part, which means we have found which part is smaller. We could just iterate over them again, recolor them, recalculate the answer, and we just discard everything we have done in the second part. And as you see, the time we have spent is just about 2 times the size of the smaller. So if this part will be much larger, so we just will not look into this at all, and we'll just stop once we have reached the end of the first algorithm. But there is a kind of, so how to actually implement it, you should be a little bit careful. To implement this kind of algorithms in parallel, it might not be enough to just keep to list of the vertices. You should also has a pointer to the current edge. Yes, so for example, if you have the vertex with a very large degree, and here also, after we switching to this algorithm, we always want to continue to look forward and never check on the edge twice. So we have to implement this kind of algorithm in parallel. We should store the vertex and the pointer to the current edge. To make sure that to get the new vertex to our queue in an algorithm, it will take us constant time to find such vertex, maybe except the edges we have already moved. So all edges that goes backwards we are not counting, and except of that we have to always to get the new vertex in constant time. So this would make us proceeding the query for the time proportional to the size of the smaller part, and using the analysis by which we can prove that for merging it is will be in total n log n. So here we have the same, it will be n log n, even if we are splitting but not merging the sets. Everything I've got for today. If you have some questions, please go ahead and ask me. So the problem, why do we need to find?
Why do we need to have the edge?
This edge, it's just the implementation thing. When you have the vertex and you will, you have BFS algorithm and you going several times stop it and make one step inside it. So you have to store what's the actually queue of the algorithm, what's the current vertex of the first, or it's the queue just stores it, right? But except our data structure queue for the algorithm, we have to store a current edge. If we have already considered all this, So once we resume our algorithm, it should already look at the next edge. You just have to skip all the edges you've already looked at the current version of the algorithm. Just implementation stuff, how to avoid cases where your BFS is just checking the same pages multiple times. And it just appears a little bit similar how the operating system works with the processes inside it. So it again has like several processes which has its own memory, and it just gives the processes several amount of the CPU resources. It's like the smaller thing that you have to simulate inside the solution. So everything that is used by the algorithm, the memory and the pointers that are used by the BFS, like this current edge, should be maintained inside, and you are not wanting to skip some important part from the algorithm. Just how I see it. I think for the next theoretical class we're gonna discuss some geometry problems. I don't know, how would you like that? So we'll just consider some maybe famous but still hard computational problems in geometry, and we'll discuss what are the optimal ways to solve. And along with the implementation stuff, how you can actually code this so that geometry would not be so painful. Okay, so see you on the contest, or if you have any questions, you can come to me in chat.